So part of what gives coordination compounds such interest and such diversity is the wide range of ligands that can participate in forming these complexes. And so we can classify these ligands in many different ways. One very useful way is to look at how many points of attachment they have. In other words, how many donor atoms are there? Okay, and so a lot of ligands are just only have one point of attachment. We call those monodentate ligands. So ammonia would be an example, right? There's a one lone pair on the nitrogen atom on ammonia. That's the donor atom. That lone pair is going to act like a Lewis base, interact with the Lewis acid of a metal at the center of a complex. But there are many well-known polydentate ligands as well. We call these bidentate, tridentate, tetradentate, pentadentate, hexadentate, etc., heptadentate, to indicate, how many binding sites there are. Okay, and so bidentate would have two binding sites. A very common example is the anion of acetylacetone, and so this is affectionately known as ACAC. Okay, this is a bidentate ligand. So basically what can happen is you can have both of those oxygen atoms acting as Lewis bases, donating electron density into a metal ion. So both of those oxygen atoms can be donor atoms and form complexes. So if you look at this, you might be seeing, oh, well, the oxygen atom on the right looks pretty different from the oxygen atom on the left. Well, there's a resonance structure that interconverts these, so that's shown here. And so really, all these bonds that the arrows are touching are 1.5 bonds. They're somewhat in between a single bond and a double bond. And so this is a conjugate system. And so, this is a symmetrical type of bidentate ligand. Okay, we usually draw it like this to show that there's some resonance in there. Ambidentate ligands, very interesting. This means that there's more than one possible point of attachment. And so you may have these ligands being bidentate ligands, or only one of the donor atoms is attaching. So ACAC is not considered an ambidentate ligand, although it is possible to only have one of the oxygens attach, and it could act as a monodentate ligand. Usually it doesn't, but it could act as a monodentate ligand. Because these oxygen atoms are symmetrical, they're equivalent by resonance. They're not distinguishable, so we don't call this an ambidentate ligand. Okay, an example of an ambidentate ligand would be thiocyanate. So thiocyanate's SCN minus, one Lewis structure that's possible is here, and you can have this bind through the sulfur or bind through the nitrogen. You'll notice there's lone pair on the nitrogen and lone pairs on the sulfur. And with kind of an older but still very common nomenclature that is used, if it's binding through sulfur, we would call this thiocyanate. If it's binding through nitrogen, we call this isothiocyanate. You can see there is a resonance structure that brings more electron density to the nitrogen. So that's what's going to be operative when you're binding through the nitrogen. So iron thiocyanate looks like this blood red complex. And in fact, it can be used thiocyanate can be used to detect blood. Sometimes I believe it is used by forensics teams to look for blood, because it's really brightens up and is a surefire sign that you have blood. If you put a colorless solution of, let's say, iron chloride or iron sulfate and sprinkle it on some blood, you'll get this nice blood red complex. But yeah, here is just showing you many different ways that thiocyanate can bind. So you can have it function as a bidentate ligand, or you can have this bridging, okay, where you have two sulfurs binding and two metals binding the sulfur, because there's multiple lone pairs on sulfur, and one binding the nitrogen, or even three okay? Because if you go back to this resonance structure, right, there's 3 lone pairs. So it's very straightforward to think about the bonding there, where sometimes you have more complex bonding. Here it's very, very straightforward, where, you know, each of these lone pairs, each of those bonds is representative of a lone pair from the sulfur donating into the metal. Here is an example of a compound, a palladium compound, where you have, you know, 2 different binding modes of the thiocyanate ligand in one molecule. So that's pretty interesting. A newer way and a better way to name the different binding modes is using kappa, and we'll use that throughout this course. And so instead of calling this thiocyanate, we're going to call it thiocyanate kappa. Kappa S, sorry, that's a typo. I'll make sure to fix this on the slides online. This should be kappa S. I got this backwards. Okay, and this is kappa N. Hopefully you can see how I got this backwards, right? We're binding through the sulfur there, so that's thiocyanate kappa S. And this we're binding through the nitrogen, so it's thiocyanate, and we'll call it kappa N. So the kappa just tells you, you know, where it's attaching through, versus using this old name of isothiocyanate. And so there's many different ligands that are quite common. Okay, you can look at different monodentate ligands here. A lot of simple ones. Okay, like I said, some of these can be bidentate, like thiocyanate. We saw some examples here. Right, that's bidentate, but it's a bridge. It's bridging 2 metals together. But most of the time, it's going to be monodentate. A lot of these simple anions that are pretty small are going to be monodentate. And then you have ones that have usually organic backbones in them, where you kind of set up these binding sites. So these are some common bidentate ligands. They have these commonly used abbreviations, like for ethylene diamine, people just call it N. Bipyridine, people call it BIPI, or just BPY, still pronounced BIPI. Phenanthylene, with 2 nitrogens there. You can see how that binds. Oxalate, carbonate, okay. And polydentate ones, triphosphate. EDTA, that's a very commonly used hexadentate ligand. Okay. Here's a little bit more on EDTA. Polydentate ligands are also called chelators. And so EDTA is pretty non-toxic. It's very, very water soluble. You can see it has these 4 negative charge. And so it's used in a lot of different environmental applications. It's actually used in something called chelation therapy. So if you get exposed to mercury or lead, I don't suggest doing that. It's a very bad idea. Okay, but the best, probably the best way to treat you in that case is to basically feed you EDTA. And what will happen is EDTA will bind up metals. That forms a very strong binding constant with lots of metals. And why is it such a strong binding constant? Well, because it's a hexadentate ligand, so it's binding the metals in 6 different spots, right? And so this will, you know, bind up all the iron, all the mercury or the lead in your body, and then that's in your blood, right? And then you can urinate it out. The problem is it also binds other things, other metals in your body that your body needs, like iron, right? And so people are very weak, and there's a lot of side effects when they undergo this chelation therapy. So bottom line is, don't expose yourself to, you know, soluble forms of mercury and lead, and you'll be fine. Some other of these chelators, these polydentate ligands, you know, they all have these very high binding coefficients because they're binding a lot. It makes sense. But you know, a lot of these other types of chelators have enforced a certain type of geometry. So porphyrin is a good example. Here shown an iron porphyrin. You can see these 4 nitrogen atoms on a porphyrin are essentially planar, and so this is a planar molecule. And so although maybe, you know, iron wouldn't want to be square planar, we're going to talk a lot about in this course what dictates whether or not a transmission metal wants to have a certain geometry. But if it has an iron porphyrin, it's basically forced to be planar, forced to be square planar, right? There's 4 things coordinating it, right? And so that's a way you can impart certain types of geometries into metal centers. Iron porphyrins are extremely important molecules in biology. Okay, so hemoglobin is an iron porphyrin. The enzyme cytochrome C oxidase, which is the enzyme that basically helps you take oxygen and electrons from food that you eat and make ATP and water. Okay, so it's a key enzyme that helps you respire. This is an iron porphyrin. Okay, so it's a really important molecule in biology.